Welcome everyone. So first of all, let's talk about why we should actually care about fast compilation. So there are mainly two user groups who care about fast compilation, especially at the level of O0. The first group of users are JIT compilers. So for example, databases, there are some databases that use LLVM or also some WebAssembly runtimes. And they use LLVM because, well, LLVM is one of the best optimizing compiler frameworks that we have. Now, when we already have one compiler backend, it also makes sense to use or try to use this as the baseline compiler, because then these systems only have to support a single compiler backend and not separate a baseline compiler backend. Another user group are developers. So if you have faster compiler, then you have faster develop test round trips, which makes you more productive. And it's also important for CIs where you care about the latency when you get back your compile errors or your test results. Now, for developer experience, this also needs to consider the compiler frontend, which I'm not going to talk about today. So today's talk will primarily focus on the backend. Now, over the last year, LLVM has seen quite a substantial improvement in the O0 backend performance of up to 18% on x86. And what we'll do in this talk is we'll look at how we got there, what are some lessons learned from implementing these improvements, and I'll also try to outline some ideas on how to make LLVM baseline compilation even faster in the future. Now, the first few things are some more general remarks on performance optimization. And the first topic I want to talk about are hash maps. So hash maps have an O of 1 average asymptotic time complexity for many of their operations, but with O of 1 neglects some constant factors, and if we access hash tables very often, then we get quite a substantial runtime cost. So it's typically a good idea to avoid hash maps if possible. And one type of hash map that occurs particularly often in LLVM are hash maps from a pointer to something else. And for this type of map, CPUs luckily have a very efficient built-in feature, which is dereferencing the pointer. So one example where we implemented this was the selection DAG combiners, which manages a work list of the nodes that it still needs to combine, and also has a hash map which maps the node to the index in the work list so that it can remove or modify items in the work list. Now, this hash map was arguably used quite often, and by storing the work list index in the node itself, instead of using hash map, it was a 1 point something percent compile time improvement at O3 end to end. So this was a pretty substantial performance impact. Now, this is, of course, not always possible. So, for example, whenever you want to map your LLVM basic block to something else, it's not always feasible to add with something else to the basic block and have all users pay for this possibly stored something else. So for this case, it's a better option when a hash map might be to use a dense numbering and an array. And this led to the addition of block numbers, which allowed us to substantially improve the dominator tree, which was previously dominated by hash table lookups. And another thing is to avoid redundant lookups of the same key in the same or in different hash tables. So for example, in the MC assembler, when creating a symbol, it was inserted into 4 different hash tables, and we were able to reduce the number of hash tables where it was that needed to be consolidated to 1, which also had quite a substantial performance impact. And as a general remark on hash maps, so while this might sound that hash maps are in itself problematic, the data structures we use, so our LLVM dense map and also the string map, are actually quite efficient data structures, but there is only so much that you can do to implement a hash map in general. The next topic I want to briefly talk about are memory allocations. So memory allocations do have a cost, especially if we have many small memory allocations. So this obviously depends on the allocator. So something like mi-malloc might be faster, but glibc's malloc, which is also, let's say, quite widely used by our users, is a bit less performant. So it's often a good idea to reduce the number of memory allocations. So one way to do this is, for example, to use a bump pointer allocator for cases where the memory usage is monotonically increasing. So this makes allocations much cheaper and also improves the spatial locality. So we did this for the MC fragments in the assembler. So fragments of machine code or data which have either fixed or fixed size or can also grow. But the downside is that this might lead to an overall increase in the memory utilization. So this is not always a clear cut. And for the future, it would be nice to have a small vector that supports bump allocator backed storage. This is particularly relevant for MC fragments, which have a small inline storage for their contents and where the fix-ups that needs to be applied. But it's always a trade-off in having a large inline buffer, which is often wasted, or in going too often into an out-of-line storage. So a small vector with a more efficient outline storage could be a good idea. And then there are a few minor general considerations. So indirect and virtual function calls have some overhead, especially if these virtual functions do nothing by default. So in such cases, it's always a good idea to try to avoid this, especially if this is done very often. So for example, LLVM MC and the AsmPrinter, they do half a dozen of virtual function calls per encoded instruction. And if some of these do nothing, then it has also a noticeable impact if the call can be avoided. Raw S-vector O-stream is another problematic case where currently every write goes through the slow path, which is a virtual function call. We try to make the slow path a bit faster, but this is still less than ideal. So ideally, we would be able to use the small vector itself as the buffer for the raw O-stream fast path and its buffering logic. Unfortunately, this is not quite easy to implement because there are a few users that depend on the raw S-vector O-stream keeping the small vector immediately up to date. So this would require adding a new type, something along the lines of a buffered O-stream. And timers are also quite expensive, even if they are disabled. So having too many timers is not always a good idea. It's also not a good idea to have them in general, but also I just want to mention that just having to check whether to keep the time is also not a free operation. Okay, so let's look at the LLVM backends. So this is the LLVM 18 state for x86 and AArch64, roughly grouped by the phases. We'll look at the individual phases in more detail afterwards. And for LLVM 20, we saw on x86 that almost all parts improved, and leading up to a total improvement of 18% on CT mark. The biggest improvements were on the AsmPrinter and the register allocator for x86. On AArch64, the instruction selector is a bit slower because global ISIL is the default at 0. And here we also saw some substantial improvements on the AsmPrinter and on the instruction selector. The register allocator changes were primarily affecting x86. And some other parses, in particular target-specific parses, got a bit slower when we were in LLVM 18. Okay, so let's look at the IR parses in the beginning. So there are 15 to 20 parses, mostly concerned about lowering intrinsics and some complex operations. But the observation is that for many functions, especially at 0, they don't have these intrinsics or complex operations that these parses handle, so they do nothing. And we started fixing this by merging some of these parses into the big pre-ISIL intrinsic lowering pass to avoid iterating over the LLVM IR so often, which is not a free operation. And I think it would be a good goal to merge these passes further so that we have in the end only one or two pre-ISIL legalization passes, so maybe one for intrinsics and maybe one for other complex operations. After these passes, the backend only primarily operates on machine IR, which is a very featureful IR and can represent machine code for the various target architectures that we support. Now, machine IR itself is not exactly efficient in terms of modifying it. And one thing that routinely shows up in the profiles is machine instr add operand. So machine instruction operands have an order, so they are first explicit and then implicit operands, and first defines and then uses. And add operands iterates over or looks for the right place where to insert the operand, and also looks up some flags, which takes quite some time. There was a consideration to add an unchecked or fast add operand, which avoids some of these search and flag changing operations, but no one has done this work yet. Another thing is that managing the use def lists of registers is also not free, but there are similar considerations that apply to LLVM IR, and I don't think this is going to change because we probably want to keep eagerly updated use def lists. Another thing is that it supports storing extra information inline and out of line for specific and rarely used functionality, but checking whether some sort of extra information is available and where it is frequently causes some branch misses that I think could be somewhat easily avoided. Okay, so how do we get to machine IR? Well, that's the job of the instruction selector, of which we have currently 3 in LLVM. So fast ISL is probably the fastest one we have because it does everything in a single step, whereas a selection deck and the newer global ISL are incrementally lower, and we write the IR until we get to machine IR. In general, there are 2 observations that are expensive and unfortunately also hard to avoid. The first thing is coil lowering. So coil lowering is a thing that shows up in the profile quite often, but I don't think that there is a substantial room for improvement there because of the various attributes and ABI details that need to be considered. The other thing is that selection deck fallbacks are and also will remain expensive for fast ISL. And at this point, it's probably recommendable for front-end authors to change the way in which we generate LLVM IR and to generate, let's say, fast ISL-friendly IR. And there are optimization remarks that they can enable to find out where fast ISL fell back to selection deck. Now, I want to talk a bit about global ISL, which has seen quite a bit of improvement over the last 2 releases. So global ISL has a multi-pass approach of translating, legalizing, and instruction selecting with combiners running in between for some optimizations. The first change was the first observation was that fixed point iteration is often not really beneficial, especially at 0. So there was an opt-in flag added to do only a single pass of global ISL combiners instead of the fixed point iteration. And this is also in line with somewhat similar earlier changes for ins combiner selection deck, where the fixed point iteration was also dropped. Another observation was that full dead code elimination is not cheap and also not always needed. The legalizer already performs that code elimination, and so combiners don't need to do this again. Okay, another change was that the legalizer didn't have it generate less bad IR for things like I1 arithmetic that is not legal, and using known bits can avoid to generate such artifacts, and known bits, even though it is not exactly cheap, is always beneficial. Even at 0, for 0 it uses a reduced recursion depth. And despite all these changes, global ISL is still 47% slower than fast ISL. It was the idea to add a fast path to directly generate target machine IR from the IR translator, but this requires some more work. And while it would be beneficial, I don't think this is coming up for the next few releases. So for the register allocator, it's a pretty complex thing. I think the main takeaway is that fast paths for the common cases are important, and likewise using fast data structures and, for example, avoiding the interaction of a sparse set by using a vector directly. I think there's also room for improvement in the way that rec units are handled. So rec units are stored as a diff list generated by TableGen. And this causes a lot of data dependencies when iterating over the rec units of a register. And I haven't measured, but I suspect that these dependencies also cause some performance overhead. When there are quite a few target-specific passes, and again, there is a similar observation that many of these passes do nothing on typical O0 input. So one change was that the O0 compilation on x86 no longer requires a dominator tree. And we changed the pass that used it to detect, to first look whether it actually needs a dominator tree and then compute it on demand. And I hope that implementing such changes will get easier with the new pass manager. Also, passes that are specific for certain ISA features like AMX should do nothing if these features are not used. So for AMX, we tracked during instruction selection, lowering whether AMX instructions actually occur. And if they don't occur, we added an early exit to these passes so that they do nothing in the very, very common case that the ISA extension is not used. Okay, so the last step of the backend is the AsmPrinter and MC, which lowers machine IR first to MC insters and then encodes this into object files. This is very flexible and highly customizable and supports various object file formats, hooking into instructions for various things, has a full assembler built into it. And for its flexibility, most of its functionality is built around virtual function calls. But it's also quite evident that it was designed with functionality in mind and not with performance. Over the last releases, Fang Wei-Song did a lot of work in refactoring MC to be more performant. So some of these changes are related to reducing virtual function calls or to reduce the number of times where data and instructions are copied. But I think there is still optimization potential when focusing on the common path, and I think there is still a lot of time spent on paths that typical O0 input does not need. Some more general consideration on LLVM backend performance. I think LLVM has a fundamental performance problem, which is unfortunately also its biggest strength, namely the incremental IR rewriting approach. Great for composability, but also very expensive. And the other thing is that compile time is often not the primary concern. So there are other concerns, for example, the quality of the generated code, the size of the generated code, maintainability, memory usage, and so on. So there is always a trade-off to be made. And the other consideration, so this was about the backend, but on the front-end side, front-end tend to generate pretty bad IR sometimes. And with the LLVM backend getting faster, we also found that Clang increasingly dominates the C++ compile time. And Clang over time tends to become slower and eat up some of the performance improvements that we achieved. So I think Clang would need actually some love. And in terms regarding the backend, so I think that a separate O0 backend, as we've been working on it, we hope to open source very, very soon, to focus on the common case that is 10 times faster than LLVM O0 would be much more worthwhile investment of time than trying to get another 10 or 15% out of the LLVM O0 backend. So to summarize, LLVM backend performance got substantially better over the last year. Many small improvements add up. Optimizing for the common path is important, but I don't think there's a fundamental change or fundamental 2x improvement coming up to LLVM. And I want to conclude by thanking all the contributors to these efforts and all the reviewers for their time and effort. Thank you.
I think I was first. So I just wanted to ask, you say the front-end time dominates compilation time. So do you mean like the whole front end from like parsing to IRGen, or do you talk just that IRGen is very slow?
So IRGen, from what I remember, is not the biggest part. The biggest part is really parsing and semantic analysis. For C++, also template instantiation is routinely a problem. IR generation is a problem for so for, let's say, JIT compilation frontends. So in our database, we spend like 5 to 10% of the compile time is spent for just simply emitting the LLVM IR. But for Clang, I think really the parsing and getting to the stage where you can emit LLVM IR is the dominating time.
Thank you.
Hi, great talk. I'm Anshu Dasgupta from Qualcomm. I had a couple of questions. So one is, a lot of the improvements that you listed didn't have much to do with O0. So do you have any data on how it affected, say, O2 compilation time?
So on x86, O2 compilation improved by 9% backend time. On ARC64, there was no improvement.
I see. And then maybe I'll have one more question, which is, have you considered having a persistent cache for something like iCell or something similar?
So we are not working on a cache. I think there are other people who do work on caching schemes. I'm not aware whether any of this is currently, let's say, in a state that is ready to use or has a clear path to upstreaming. I'm not aware of any of that.
Thank you.
Hey, you mentioned that timers, even when they're not active, can be really expensive. But I think it's a really big problem in compilation time that programmers don't have any visibility into where the time is going. So I find tools like TimeTrace to be really helpful. I've just been using them recently. So do you have any, if timers are expensive, do you have any ideas on how we could provide programmers more visibility into what the compiler is doing so they can actually engage in the process of optimizing their own builds?
Yeah, so I think that the problem is if you place the timers in a too fine granular way. So for example, one timer per instruction. And I think these timers also don't really help because at this point, the measurement overhead also makes your results less valuable that you get from the timers. So I think for, let's say, higher granularity things like passes or analysis, I think it's great to have, and a time trace also has a pretty low overhead, so I think it's only 2 to 3%. So for this, it's pretty great, and for other things, I've had some success in compiling LLVM with frame pointers and using profiling tools. So this is typically my way to go for things that don't show up in timers.
Very interesting talk, thank you. You mentioned that in Clang the front end dominates, and this actually matches our experience. I'm curious, what would be your top 2 things on the front end side? Do you have any thoughts on top 2 hotspots there?
So I don't think I ever committed to Clang, and I'm not exactly familiar with the code base. I think, so intuitively, I think the AST is not as good as it should be. And I think it's a pretty expensive data structure. I think it's possible, at least for C, to write much faster, have a much faster approach, to write much faster compilers. For C++, I have no idea. I've never wrote my own C++ compiler.
Thank you.
Have you thought about code gen each function in its own thread, or it's a crazy talk?
So parallelism with LLVM is very difficult to achieve because everything is basically munched into one single context. We thought about it a bit, but so as I briefly mentioned, we have instead opted to write our own LLVM backend, which handles the common case 10 to 20 times faster. And if we are 20 times faster, then I don't think parallelism is that important if you still have the parallelism over translation units.
Well, and for JIT, it probably doesn't matter because it will be one function anyway, but for big project where CMake run stuff in parallel, it also doesn't matter. Maybe there is a sweet spot, but
Yeah, so I haven't done any analysis on at which points a multi-thread in the compiler would be a good idea at this point.